In this video, I'm going to try and cover all of the mechanisms that you need to know for AQA A-level chemistry. Do it in one video. Okay, so I've divided. These are the four mechanisms you need. There are others as well, but I'll do these just to summarize. Nucleophilic substitution, and this square here, then that is the we're talking haloalkanes. I'll just put down Bromo Ethane, and they can react with OH minus, or with ammonia, or with the cyanide ion. Okay, so we need to know all of those. The electrophilic addition was the next one you did. This is a year 12 one, so that's the reaction of an alkene with HBr, with conch sulfuric acid, or with Br2. Nucleophilic addition, probably end of year 12, year 13. It's not on the AS, it's on the A-level part. That's a reaction of an aldehyde or a ketone. So you've got a delta positive on that carbon there, with either a hydride ion, H minus, or a cyanide ion, Cn minus. Okay. Then the final segment here, electrophilic substitution, that's with a benzene ring, and that's with NO2, or it can be with an acylium ion, which you've made from an acyl chloride and aluminium chloride catalyst. Okay, there's those four, and then there are others here. There are nucleophilic addition elimination, that's with to make an N-substituted halide with an acyl chloride, and either an amine or an alcohol reacts with either of those. Elimination of HBr, that's from a haloalkane, the year 12 one. And then finally, dehydration of an alcohol to an alkene. So I'll probably do them more or less in that order. Okay, so right, let's start off with nucleophilic substitution, which is probably the first one. Right, so you've got a haloalkane. Right, so let's have Bromo Ethane. We have a partial positive charge on the carbon there due to the electronegative halogen. And let's have, first of all, let's do with an OH minus ion. So there's 3 lone pairs in the oxygen. I'm only going to draw 1 negative charge on that. All that happens is that pair of electrons goes onto there. The pair of electrons in the carbon halogen bond breaks, and that gives you the alcohol as the product. And the Br minus, that one is pretty straightforward. If you do it with a cyanide ion, it's exactly the same. It's pretty easy. I draw my cyanide. Let's draw a cyanide to show the bonding in it. So you've got C with a triple bond N. Got your lone pair on the carbon, negative charge. That is going to go onto there, and the bromine is going to drop off as exactly in the other one, and you'll end up with now you call it a nitrile, and you made the carbon chain longer, which is very useful. Okay. Finally, let's do it with ammonia. Actually, I will come back to this one a bit later as well. Ammonia is pretty similar to these, just a little bit more complicated. So we've got our bromine on there. Delta positive on the carbon. Now the nucleophile is the ammonia, and that's because it's got a lone pair and a very electronegative element, nitrogen. Okay, so that is going to, actually I will draw that out with 3 hydrogens. I'll show the bonds. Okay, so that lone pair is going to go onto the carbon. The carbon halogen bond is going to break, and we are going to form this intermediate. Okay, and that has, right, that nitrogen has now got a positive charge on it. And the final step is for one of these, the pair of electrons in the hydrogen in the pair of electrons in the nitrogen hydrogen bond is going to go back into the nitrogen. It's going to become a lone pair instead of a bonding pair to give you the amine. Okay, so we've got just 2 hydrogens stuck to the nitrogen. Now, in reality, this hydrogen won't come off as H+. It will be picked up by another ammonia. So that you should really draw that, but the mark scheme, they don't need you don't need that bit. So you should show that, and then that of course will come off here as NH4+, but they don't actually require you to do that. So just keep it simple and just have it show the hydrogen dropping off as H+. Okay, I will come back to that one later at the end of the video, because of course this amine is still a pretty good nucleophile because it's got a lone pair on it, and that can undergo further substitutions, but you don't really cover that till year 13, so I'll leave that till a bit later, just the extra bit there. And now let's move on with electrophilic substitution. Sorry, electrophilic addition, which is probably the second mechanism you did in year 12. Electrophilic addition. So we're talking here about alkenes. I'm going to draw propene because it makes a difference if you've got an asymmetric carbon atom. You probably remember this because there's a possibility of 2 different products forming. Okay, so I'm going to draw that just as CH3 at the end there to save a bit of time. So there we've got propene, and that's going to react with hydrogen bromide is the electrophile, the simplest one. So here's HBr. Now we've got a partial positive charge on the hydrogen there because bromine is more electronegative. We've got high electron density in that double bond. We've got a sigma bond and a pi bond, and that's going to attract the hydrogen. Okay, so what's going to happen there is the pi bond electrons, they move onto the hydrogen. Curly arrow there. That hydrogen will then be forming too many bonds, so we've got to break the one between the hydrogen and the bromine. The electrons go to the bromine. The hydrogen can actually then attach to either the green carbon or the yellow carbon. Right, so let's see what happens if it attaches to the green carbon. Sorry, I've got too many hydrogens on that carbon there. Sorry about that. The really bad carbon with 5 bonds. If it attaches to the green one, what's going to happen there? Well, so I'll do that. We form this carbocation. There's a carbon there. This carbocation, and you can see that this is a primary carbocation. Well, if it attaches to the other one, you see you'll get a secondary carbocation. So if it attaches to the yellow carbon, there's our new hydrogen stuck on there, and we have a carbocation. The carbocation is on the middle carbon here, and this is a secondary carbocation. Now this is more stable than the primary, so it tends to form more, so you get more of this secondary carbocation forming. And so that is then going to react with this is the bromide ion, which has come from the hydrogen bromide, Br minus. and one of the pairs, lone pairs, goes onto the carbon to form a bond. So you're going to end up with two bromopropane, and this happens more. So this would be called the major product. To get more of that one, and this one, which goes through the primary carbocation, you get less of it. And so you're going to call that the so the bromine, draw here, that goes onto that carbon there. You're going to get the 1 bromopropane, which is called the, you say that is the minor product. You get less of that. Okay. Right, let's do electrophilic addition. So that we've done that with HBr, we also need to know about electrophilic addition with Br2 and with concentrated sulfuric acid. So I'm just going to very briefly draw those two. Okay, so the difference with the Br2 is, of course, that bromine Br2 does not have a permanent dipole. Okay, so why does it react? Well, the reason why it reacts is because you get an induced dipole. Right, you get an induced dipole. This bromine will become delta positive, and that's going to become delta negative, because you've got all the negative charge in the double bond, which is going to repel the negative charge sort of down this end of the molecule. And then the reaction mechanism then is exactly the same. So I won't actually complete it. But you know, the first step in the mechanism is going to be, that's going to go into the bromine, that bond breaks, and then you're going to dibromo ethane as the final product. Let's do what happens with concentrated sulfuric acid. It's exactly the same as with HBr, but the sulfuric acid just makes it look a bit more complicated. So here we've got our ethene, and here's the structure of concentrated sulfuric acid. So this displayed formula, you're going to have two double bonds. Right, that, well, won't either hydrogen, but that hydrogen is going to have a partial positive charge on it because the oxygen is more electronegative. The mechanism at first, that goes onto there, the pi bond breaks, and the bond between the hydrogen and the oxygen breaks. The oxygen gets both electrons, so you're going to end up with a carbocation intermediate. It's exactly as you did with HBr, and you end up with this hydrogen sulfate negative ion. A negative charge on there, and that pair of electrons is going to react with the carbocation to form the sulfonated compound with the hydrogen sulfate stuck to it, and that then can react with water to form an alcohol. That's why you're interested in that reaction. But there's that sulfonated intermediate, which will react with water. Okay, so that's electrophilic addition done. Now on to nucleophilic substitution. Nucleophilic addition, sorry, which you probably do. It's not on the AS, as I say, it's at the start of year 13 or the end of year 12. Nucleophilic addition. Okay, we're going to start off with an aldehyde or a ketone. I'll draw ethanol, keep it simple. Right, and it can react either with a hydride ion or with a cyanide ion. I think I'll draw cyanide here. Right, you have a partial positive charge on that carbon because of the electronegative oxygen, and you've got negative charge on a cyanide ion. Right, the first step in the mechanism, the lone pair on the carbon attacks the carbonyl carbon. The pi bond then breaks, both electrons go into the oxygen. So the intermediate we're going to get is we've got an O minus here now, and we've got the cyanide group which is stuck on there. Now the O minus we just show it picks up a proton, an H plus from the solvent. So I need to draw a lone pair of electrons there, and that pair of electrons goes onto the hydrogen, and you're going to form what becomes an OH group, and you've got the final product, that's a hydroxynitrile. And what's worth mentioning here, I chose the cyanide. That is an asymmetric carbon now that can show that's chiral. And the product you get, you don't just get one isomer, you get a 50-50 mixture of both optical isomers. You get a racemic mixture, and that is because the nucleophile attacks either from above or below. If it attacks from above, this is a flat planar structure. If it attacks from below, you're going to get one optical isomer. If it attacks from the other side, you get the other, and both are equally likely. So you end up with a racemic mixture. Okay. Now with the hydride ion, it is exactly the same. It's more simple there, and I won't draw the whole mechanism, but the hydride ion is the hydride ion attacks that. I should draw it the same way around as I drew it before. Right, hydride ion, which comes from, so it's a hydrogen with an extra electron, and that is from sodium borohydride. Really, it's not a hydride ion by itself, but you're allowed to, they expect you to simplify it, just showing it as a hydride ion. That attacks the carbon, that goes to there, and of course you will end up there with a primary alcohol, in that case, as the product. And it's also a reduction, that reaction. So they're the two nucleophilic addition mechanisms you need to know. It's the same one really, just the cyanide ion or the hydride ion. Right. So that's our four basic ones. Now we are going to go on to one which is probably the most complicated mechanism that you need to know, of nucleophilic addition followed by elimination. Now this happens with acyl chlorides. It can also happen with carboxylic acids, okay? So, but the carboxylic acids don't react quite as well. Of course, the only difference with the carboxylic acid, of course, is instead of a Cl attached to the carbon, you've got an OH there. They're not quite as reactive, right? And it can react with an amine or an alcohol. So let's draw an amine. In green. So here's an amine. I'll draw methylamine, the simplest one. I'll draw. Okay, now we have a partial charge, positive charge on the carbon there, due to the electronegative oxygen. And we've got a lone pair on our nitrogen, which is pretty electronegative. If that's an alcohol, it's an extremely similar reaction. All that happens there is, draw methanol, you've got a lone pair on a very electronegative atom there, oxygen instead of nitrogen. So the first step in the mechanism is that attacks the carbon, okay? It forms a bond to the carbon, so that means the pi bond here has got to break. It breaks, and we're going to form this intermediate. Right, we've got a negative charge on the oxygen. Our chlorine is still attached, and we have now got the nitrogen. I've still got two hydrogens attached. Now the nitrogen is forming four bonds, but the giveaway that it's going to have a positive charge on it. And what happens next is the pi bond reforms. So I've only drawn one lone pair on that oxygen. It's obviously got three. That lone pair goes back to reform the pi bond that had broken before, and that carbon will be forming too many bonds. So the chlorine has got to go. Okay, so that comes off as a chloride ion. Now, if this was the alcohol, you can see that if this was a carboxylic acid, you can see that all that's going to happen is you're going to lose the OH minus instead of a Cl minus in that step, but it's exactly the same. Right, let's draw the next intermediate. So we've got CH3, we've got our carbonyl group back. Cl minus has fallen off, and we have our nitrogen there with positive charge. And the final step in the mechanism, again, you should really show that that hydrogen being accepted by the amine, but it's okay just to draw it as falling off by itself. So that pair of electrons is going to go back to form a lone pair, and you are going to form we've lost one of the hydrogens. I should draw it the one. Okay, and that is called an N. That is now an N substituted amide. That is the nucleophilic addition elimination. And if you do it with an alcohol instead of an amine, then you're going to get an ester formed instead of an N substituted amide. You get, just to draw it down there, you're going to get that, which is an ester. Okay, but essentially it's the same mechanism. Right, so that's that nucleophilic elimination. Let's do now the elimination of a haloalkane, which is actually a year 12 one. Let's do a haloalkane. So here we've got Bromo Ethane. Now, just to remind us what actually happens in the final step, I'll rub this out in a minute. You form ethene, you form an alkene, and that occurs because you lose the bromine and you lose the hydrogen on the carbon next door. Okay, it's not on the same carbon, it's on the one next door, and you're going to form a double bond there. Right, I'll get rid of that. Now, this is, you have to be careful here because use the same reagent, use sodium hydroxide as you do for nucleophilic substitution. But instead of having it dissolved in aqueous solution, you have it dissolved in ethanol. And the OH minus then is not going to behave as, doesn't behave as a nucleophile, it behaves as a base. So, right, here we got OH minus. It doesn't attack this delta positive carbon if you use the ethanol. It actually acts as a base, a proton acceptor. So it accepts, draw a lone pair there. It picks up this proton to form water. Okay, so that hydrogen is gone and leaves its electrons behind. That pair of electrons in the carbon-hydrogen bond go to form a pi bond there. And of course, this carbon is now going to be forming too many bonds. So the bond between the halogen and the carbon breaks, both electrons going to the bromine. So there's 3 curly arrows and 1 step there. It's just 1 step, no intermediate. We're going to get that. Br minus is going to drop off. And we've also formed a water molecule from the OH. Okay, so that is elimination. Okay, that was elimination. Now, pretty similar to elimination, and that you form an alkene as a product. We're going to talk now about dehydration of alcohols. Okay, this is a year 12 one as well. Okay, so now let's start off with ethanol. And it is very similar to the elimination of HBr, because we're going to lose an OH from that carbon and a hydrogen from the one next door, and we're going to form a double bond there. We're going to form ethene. That's what's going to happen. Okay, right, now we need an acid catalyst for this, so I'm going to draw H plus. You don't need to draw use conch sulfuric normally, but you don't need to draw that. Okay, it's okay to just draw H plus. You get all the marks right. Right, so what happens? We've got a lone pair on, two lone pairs on oxygen. You just draw one. That transfers, a pair of electrons go there to form a bond to the hydrogen. Now, if you wanted to show it with that, then you'd show that this bond then breaking to form that negative ion, but we're not going to bother doing that because we don't need to. Right, so we're going to form an intermediate. Like that. Now that oxygen has got a positive charge on it because it's picked up the proton, and that tends to withdraw electrons from this carbon here, and that's what sets off the whole mechanism. So what happens is, right, that pair of electrons goes to form the pi bond, and the pair of electrons in the carbon-oxygen bond are taken by the oxygen to form water. So you get the alcohol as a product. So the alkene is a product, formed a double bond there, and we get water. And this hydrogen here, well, that will have come off as H plus. So you can see that H plus acts as a catalyst because it's used up in the first step and then gets regenerated in the second step. So that's dehydration of alcohols. The one I haven't done yet is the electrophilic substitution, which occurs with a benzene ring. Okay, so here's our benzene ring. The two electrophiles we need to know about are NO2 plus, and of course, if you remember, you generate that mix with a mixture of conch nitric and conch sulfuric acid. That generates that. So you need to know the equations for the generation of that. Or the other one you could have is you could have an acylium ion. That's the simplest acylium ion. That has been generated from ethanoyl chloride using an aluminium chloride catalyst. So you need to know how both of these electrophiles are formed. Right, so let's do it with NO2. First step in the mechanism is a pair of electrons jumps out of the delocalized system onto the nitrogen and forms a bond to it. So that means, let's show the nitrogen attached to attached to that carbon. So we've got NO2 stuck on there, and that means the delocalized system is partially broken. So I'm going to draw it like that. So you should draw it being broken from that carbon to that one. Get rid of those lines. Right, there is a positive charge which is delocalized over the benzene ring, which makes it stabilizes the positive charge, and we usually show that remind ourselves there's a hydrogen. There's obviously a hydrogen attached to every carbon. We just draw that one in. Now the final step in the mechanism is for the pair of electrons to come out of this bond back into the benzene ring to reform the delocalized system. Okay, so the final product is just that. We've got our delocalized electrons back again, and we have an H plus ion from the hydrogen that's dropped off the benzene ring. That's electrophilic substitution, a pretty short mechanism. Okay, so that's covered everything. The only thing I haven't talked about, and I said I'd come back to it, is with the nucleophilic substitution with using ammonia, okay, with a haloalkane. Right, so as I said earlier, well, you get let's say we get a bromo ethane. Just draw it like this. That's going to react with ammonia. So the lone pair goes onto the delta positive carbon. The halogen atom comes off. There's the halide ion. So we've got that. We've now got a positive charge on the nitrogen, which we're going to lose because we're going to lose a proton. So that pair of electrons there goes back in there. So we've formed now a primary amine. But the primary amine is a good, is also a good nucleophile. So that can react with another molecule of a haloalkane. So I'll draw that up here in red, CH3, CH2, and I'll just draw it like that. So that pair of electrons can go onto there, lose another halogen. What we can see what we're going to form there is we have formed we've still got, do that in green. We've got two hydrogens attached to our nitrogen, but we've now got another CH3, okay, that group there, and we've got a positive charge on our nitrogen, and that can then lose one of those protons. So just draw that. So the pair of electrons is going to go back into the nitrogen, and we've got a secondary amine. Right, now the secondary amine is also a pretty good nucleophile. We've got a lone pair on the nitrogen. So that can then undergo another round of nucleophilic substitution to form a tertiary amine. So the tertiary amine is like that. I won't draw the whole mechanism out, but you get the idea. And the tertiary amine is still a good nucleophile because you've got a lone pair on the nitrogen there, which can then pick up another round of substitution, and that is, so I'll rub that out. Then you form you've got a fourth alkyl group attached on there. You've got a positive charge on the nitrogen, and so that you've formed a quaternary ammonium salt. Now, if you want to get the quaternary ammonium salt, you use an excess of haloalkane. If, on the other hand, you want the primary amine, you just want one substitution, you want to stop it at the primary amine here, you make sure that you've got an excess of ammonia. Right, that's all the mechanisms for AQA chemistry in one go. Bit of a rush, but there you are.